This is the IME 450 Fixture Design Project, presented by Luke Martin and Jacob Blair. We were tasked with the objective of creating a fixture plate specifically designed for the manufacture of a Cal Poly dial holder. The creation of a fixture for a specific component is advantageous because of the increase in manufacturing efficiency due to the decrease in cycle time. This is largely achieved through the decrease in time for load in and load out, as well as the standardization of the working coordinate system between job ops. Therefore, as the quantity of manufactured components increases, so too does the advantage of having a specific fixture designed for that component. Our solution approach is as follows. Starting with the constraints, we designed the fixture plate using SolidWorks, and then doing force calculations in FEA proving out our design. Afterward, we created and generated tool paths using HSMWorks, and then machined the part on a Haas VF2 machine. After that, we assembled the fixture plate using the Mighty Bite clamps and rails, as well as dowel pins. Once this was completed, we qualified and installed the fixture plate into one of the Haas VF2 machines, and machined the final component using the fixture plate to proof out the fact that it worked. Beginning with the constraints of the project, we start with a fixture base size of 5/8 by 5.5 by 10 inches of Mike 6 tooling plate. This fixture plate must be able to mount to the Haas CNC mill table and also needs to be able to be indicated parallel to the CNC machine's axes. The fixture must be capable of producing one finished part per loading cycle. It also needs to be able to qualify the datums for the component during Operation 1 and locate the part off of those datums for Operation 2. The fixture load and unload time must be under a minute. The CNC blank size is 1.25 by 2.5 by 3.55 inches length of cut. The clamping forces must be able to withstand the tooling forces with a minimum safety factor of 2, and the fixture must be assembled with the available Mighty Bite supplies and dowel pins. The design of our fixture begins with the indicating band near the top of the fixture plate. This is a qualified surface that will be used to indicate the fixture into the CNC Haas machine. The rail pockets are machined to 1 thou oversize for a tight slip fit with the Mighty Bite rails, whereas the dowel pin holes are slightly under-reamed for a 1 thou interference fit. The tool plate is the primary locating feature of the fixture, whereas the Mighty Bite rail is the secondary and the dowel pin the tertiary locating feature. The dowel pins are located to the right of the workpiece in each operation due to a recommendation from Mighty Bite because of the clockwise rotation that causes the clamping force. Operation 1 is rotated 90 degrees in regards to Operation 2 so that the length of cut of the workpiece is located off of the tertiary datum instead of the secondary datum. A relief pocket is designed for the Mighty Bite clamps in Operation 1 so that the cutter does not run into the clamps during the bottom of its tool path. Side slots are machined into the tool plate in order to clamp the tool plate to the CNC table using T-slots and socket head cap screws. Finally, chamfers and fillets are added to the outer edges of the tool plate for safe handling. The tool plate was designed for manufacturing in such a way that every single feature could be machined in one operation. This operation was done on the VF2 Superspeed. After which, the fixture plate was fully assembled using the proper rails, Mighty Bite clamps, and 3/8 inch dowel pins. After being tested against an indicator gauge and clamped to the CNC table, we cut our workpiece and began machining for Operation 1. This operation would qualify the datums that would be used to locate for Operation 2. Operation 2 consists of machining off the extra stock left by Operation 1, machining the main pocket for the dial, and engraving the Cal Poly logo. Based on visual inspection as well as confirmation from Treon, our tooling was able to fixture both operations properly and produce a quality part to spec. It was expected that our fixture would be able to properly hold the workpiece because of the fact that the maximum cutting force that we computed for these operations was only around 25 pounds tangentially, whereas the Mighty Bite clamps were able to clamp with a force of 800 pounds. While our design satisfied all of the criteria for the project, there are still several ways that the design could be improved upon. First and foremost, the location of the Mighty Bite clamps in Operation 2 did not take into account some of the tool paths near the bottom of the operation. This caused those Mighty Bite clamps to be eaten into during machining. A similar issue occurred with Operation 1, However, this was not a design flaw, but a mistake in the Mighty Byte solid model. To summarize, our team followed the solution approach of starting with solid modeling, then CAM, then machining, then fixture assembly, and finally testing. To further improve fixture design, consider the aforementioned clamp location issue. Also, consider the symmetry of the fixture plate for aesthetic reasons. Lastly, consider machining in titles or instructional labels to reduce technician error. However, even without these design improvements, our fixture design was able to satisfactorily meet all of the requirements and constraints for this design project. Our team learned much about the design and fabrication of fixtures in industry through this project. Thank you for watching.